Bon. Bonjour, bienvenue à tout le monde. Mireia et Leon-Dasi, vous avez soumis un manuscrit, le volcanisme explosif sur Mercure à travers la télédétection, les études de laboratoire et l'apprentissage profond en appui à la mission Bepi-Colombo. Les deux, la rapportrice et le rapporteur, ont revu le manuscrit et vous ont autorisé à soutenir. Donc, nous allons pouvoir vous en écouter pendant 45 minutes. Et devant le jury, qui est constitué donc à distance de Nancy Chabot, qui est Senior Researcher à PSL aux États-Unis, Patrick Pinet, qui est rapporteur, directeur de recherche émérite à l'IRAP, Université Paul Sabatier. Nous avons aussi Kathleen Nance, astronome adjointe à l'Institut d'astrophysique spatiale à Orsay, Fabrice Cipriani, qui est à l'ESA, Senior Researcher à l'ESA, voilà. Sylvestre Maurice, astronome à l'IRAP, Université Paul Sabatier, les deux directeurs de thèse, Sébastien Besse à l'ESA et Alain Doris Undiram, ici au LIRA, et moi-même, Thierry Fouché, professeur à Sorbonne Université. Donc, Mireia, c'est à toi. The floor is yours for 45 minutes.
Okay, let's see if this works. Yeah. Okay, thank you for the introduction. Today I will present my PhD work on explosive volcanism on Mercury. And for this, we've been using spectroscopy from both remote sensing and the laboratory to support Bepi-Colombo. And in this presentation slide, you can see one of the latest images of Mercury taken by Bepi-Colombo on its last flyby. And here you can already see here in the limb the explosive volcanic features that we'll be talking about here. So let's get into it. And to start the presentations, I would like to put the exploration of Mercury in the context of the solar system. And as you may know, Mercury is part of the inner solar system. And while the distance to the Earth is not much larger compared to Venus or Mars, the time it takes to get to the innermost planet is in the order of years instead of months. As a result, the exploration of Mercury has been much more limited compared to other bodies such as Mars or the Moon. However, it is a very interesting body that has suscited the interest of many explorers. The first mission to explore Mercury was the Mariner 10 mission from NASA. And this mission, in the 70s, it performed 3 flybys of the planet. And with its 7 instruments, it allowed to already image 45% of the surface, and it discovered the presence of volcanic features. And we can see here an image of this map of Mercury. It wasn't until more than 30 years later that NASA returned to Mercury, in this case with an orbital mission that spent 4 years in orbit about Mercury. And with 9 science instruments, it allowed to image the surface at higher resolution and also perform color maps of the surface, as we can see here, of 99% of the surface. And in this case, volcanism was confirmed and tectonism was also confirmed. So let's start with a brief introduction of Mercury, going from the interior to the exterior. Mercury is characterized by having the largest uncompressed density out of the bodies in the solar system. And this is mostly due to the very large core. So as you can see here, compared to the Earth has a core of about less than half of the planet radius, while Mercury is about 75% of the planet radius. Moreover, the planet has been cooling and contracting from its beginning, and this is due to the small size of the planet. Regarding the surface, as you can see here on the monochrome image from the MD's camera on board Messenger, visually it's quite similar to the Moon. It is dark, it is heavily cratered, and it has evidences of tectonic features and also of volcanism. And here you might not be able to see all of this, but if we look at it with the enhanced color map, this is a false color image that I will show throughout the presentation, created from the MD's camera as well. We can see some spectral differences. And we can already see the presence of the ejecta rays, the hollows that I will briefly discuss, and also explosive volcanism. Regarding the exterior, Mercury is bonded by a magnetosphere and an exosphere, and both of these structures will impact how the solar wind and the space environment interact with Mercury's surface. So overall, these missions have made many discoveries, but there are still mysteries regarding the exploration of Mercury. There are mysteries regarding the origin of the planet, the activity, whether it is still active, there's a volcanic history. Also, we have measured that it retains a magnetic field, but it is still unknown how is it able to retain a magnetic field, and also to understand how it is affected by space weathering. The observation of Mercury has been contrasting with the expectations that researchers initially had of the planet. Initially, one of the biggest expectations was that Mercury would be depleted in volatiles. And the reason for this was that it was thought that Mercury would have formed at very high temperatures, either in the inner solar system, in the inner solar nebula, or because it was brought inside by a giant impact that would also implicate a lot of heat. However, the observations of Mercury reveal that the planet is actually high in volatiles, it's rich in volatiles. We can see here this plot of the potassium to thorium ratio, which is a ratio of a very volatile to a refractory element. And we see how when we go inside in the solar system, the volatile abundances decrease. And when we would expect Mercury to be around here, it is higher up actually. Mercury is rich in other volatiles such as sulfur, and it actually has higher abundances than the Earth or the Moon. And the expression of volatiles in the surface is also present in other features, such as the hollows, which is unique to Mercury. These are depressions, flat depressions on the surface of Mercury that are thought to be created by the volatilization of volatiles. We have volatiles in the ice deposits and the poles, and also we have volatiles in the exosphere. So we have a first expectation that was not found in the observations. Related to the volatile abundances also, volcanism was not fully expected. So during the Apollo era, the presence of effusive volcanism on the planet was contested, and this was mostly due to the strong difference that we see on the Moon between the effusive volcanic regions that have a lower albedo than the rest of the Moon. And we don't see this contrast on Mercury. The Mercury surface is more homogeneous, and as a result, effusive volcanism was contested. And as for explosive volcanism, it was directly not expected until it was observed. And however, again, observations don't match these expectations, and we find that Mercury is covered by widespread effusive volcanism and global explosive volcanism. Another expectation for the planet was that it would be inactive. The first reason for this is that since the planet is cooling, it was thought that the magma supply would decrease due to this cooling, and also the cooling would result in a contraction that would restrict the ascent of magma. Moreover, it was thought that the iron core would solidify early on. However, once again, the observations don't match these expectations. And in Mercury, we have found the presence of an internal magnetic field that together with the gravity measurement means that there should be a fluid outer core on the planet. Moreover, there have been observations of recent tectonism, which support that the planet is still slowly cooling. And the features that we were discussing before, the hollows, could be still forming in the present. Therefore, this expectation of no activity is also rebated. And again, related to volcanism, activity, and by comparison with the Moon, initially it was expected that volcanism would stop after the global contraction period, so after 3.6 gigayears ago. However, we have been observing this gap between the observations and the expectations, and therefore in this thesis we want to explore this gap and try to understand better the timing of explosive volcanism on Mercury to understand what this tells us about the planet. The reason to explore volcanism is because it provides an input for the interior thermal models and also planetary formation models, and it refines our understanding of planets forming close to their star, which is particularly important for exoplanets. On Mercury, we have two different types of volcanism. On the top row, you have effusive volcanism, which is the formation of large plains of lava that form through these lava flows. And you can see a similar flow already solidified, of course, on Mercury, as you can see how it flows toward this area. The second type of volcanism, which is the one that we're interested about, is explosive volcanism. And we can see here an explosive volcanic eruption on the Earth and the result of an explosive volcanic eruption in the past on Mercury. So going more into detail with explosive volcanism is the result of violent eruptions that involve gas, and they produce ash and these fragmental debris that we call pyroclasts. So on Mercury, these eruptions are characterized by two different features. We have the vents, which are the irregular depressions that do not have a raised rim by which the eruption occurs. And we can see here the example of two different vents, the same vent actually, seen from above and from the side. And you can see how it is quite irregular, and we can distinguish them from craters from their shape. Surrounding the vents, we have the deposits of pyroclasts that are produced in this eruption. And they are characterized, as you can see here in the false color images, by having diffuse margins. You can see how they mix with the background terrain. And generally, they have a high reflectance and a red spectral slope, and they have this color, orangish color in the false color images. And you will see in a bit why I say usually. We have been talking a bit about spectra, so let me discuss the spectral units on Mercury. On Mercury, Mercury's surface is characterized by being very dark, and the spectra is usually characterized by having a red spectral slope, as you can see here for the major units, which means that the reflectance increases towards longer wavelengths. And in general, the major units are absent of absorption features, as we can see. So the major units going from higher to lower reflectance are the high reflectance red planes that we see inside this basin called calories. The intermediate planes, then we have the low reflectance blue planes that we see going around calories, and the low reflectance material that in this case is poking through this crater. As we can see, these units are mainly distinguished by their reflectance and their slopes. However, there are different units on Mercury that have different spectra. And we have some minor units such as the fresh craters and hollows that we can see here in these bluish tones that are characterized by having this curved part in the visible part of the spectra, and also pyroclastic deposits that we will discuss, which in the false color images have these red tones, and as we can see, they can present different spectra. So overall, this brings us to our two first research questions, which are to understand what is the extent of pyroclastic deposits on Mercury, and if there is a unique spectral signature of these deposits. Regarding the timing of the eruptions, which we have said that it's important to understand the thermal history of the planet, while for effusive volcanism, it is pretty well understood that the activity almost decreased after the global contraction, for explosive volcanism, the timing is more unknown. So there is evidence of these eruptions happening up to 3.9 gigayears ago, and some eruptions in early craters that date around 1 gigayear ago. However, the pace of eruptions in this period is unknown, and whether there are eruptions before or after this period is also unknown. And therefore, what we want to explore is how the spectral properties of these deposits evolve over time, and what this tells us about the timing of these explosive volcanic eruptions. I have talked about the spectral units on Mercury, but on Mercury, there are also different geochemical units. So overall, Mercury relative to the moon, it is richer in sulfur and in magnesium, and it is poorer in aluminum, calcium, and iron. And it is this lack of iron what is thought to cause, or to be one of the leading causes of the lack of absorption features on Mercury. And here you can see the geochemical regions on Mercury and compared to a magnesium map, and you can see how they are very similar. So the geochemical variability is dominated by the magnesium variability. However, as I mentioned, there is a difference between the geochemical units and the spectral units. And therefore, to understand how different the geochemical units or different terrains with varying magnesium variability are measured with spectroscopy, for this, we can use the lab. So in this work, we will use laboratory measurements and in particular reflectance spectroscopy as a way to understand better the remote sensing measurements. Reflectance spectroscopy is a measure of the reflected light by the surface of a body, and it provides information on the composition and mineralogy of this body, on the physical properties such as the grain size, on the temperature of the surface, and also on the space weathering that the surface has undergone. And by space weathering here, we mainly focus on the effect of ion irradiation and the bombardment of micrometeorites. In this work, we use laboratory spectroscopy first as a means to prepare for the Bepicolombo mission, and in particular for symbiosis, and second as a way to replicate the in situ conditions that are present on Mercury to understand the observations from remote sensing. So this brings us to our last two research questions, which are to understand what are the evolutions of a Mercury analog measured by laboratory spectroscopy, and also what are the effects of varying the physical and environmental conditions of the analog on the spectroscopy. So to summarize, we have our first research question, which is related to our first paper. The second and third research questions regarding the timing of the eruptions, which are related to our second paper. And the fourth and fifth questions related to laboratory spectroscopy, which are linked to our third paper, which actually has been accepted this week for publication. In this work, we use laboratory spectroscopy and also remote sensing. And for remote sensing, we use the data from the messenger masks instrument. This is a point spectrometer on board the Messenger mission, and you can see here the instrument. And it measures reflectance from in the UV to the near infrared, covering from 300 to 1,450 nanometers with a 5 nanometer spectral resolution. These spectra, we retrieve them from the MES database, which is a database containing almost 5 million spectra that have, and the benefit of this database is that the spectra are already corrected and that we can filter them by viewing geometry, instrument parameters, and measurement parameters. And with this, we can remove the observations that are taken at very high incidence or emission angles, also the observations taken at high temperatures, which are more noisy, and remove the large footprints. And here you can see an example of how we have different tracks of the spacecraft with the different footprints, and we remove those here that are going through the shadow and the very large footprints here. So with this, we start with the first question. And we want to explore the extent of these explosive volcanic deposits. So there are several research that have tried to understand the extent of the deposits, and they have found several challenges. First, as you can see already from the false color images, there is a large variability in the spectral properties of the deposits. So if we wanted to distinguish them by a given color, it would be quite difficult because we have some that are very bright like this one and some that are a bit darker. Moreover, some of these works have defined the extent of the deposits as circular, and we can see that in many cases, the deposits are highly irregular, as we can see here, and this is because they are formed by overlapping eruptions from different vents. And finally, if we want to study the shape of the deposits or explore the extent from the MDIS images, this can lead to an underestimation, since, as you can see here, we have the deposit as defined by Kerber et al. With MDIS. And if we look at the deposit with different channels from the MASC's instrument, we see that the apparent extent will be different. Therefore, there are nonlinearities in the data that are difficult to explore by hand and with just one data set. And this is what prompts us to use deep learning to treat this problem. We use deep learning for two reasons. First, because we can treat very large data volumes in an unsupervised way. And second, because we can detect complex features that are nonlinear. And I will not go into detail on the training process and the preprocessing process, but feel free to answer any questions later on. And in our case, we use a three-dimensional convolutional autoencoder. This is an unsupervised network, and the main advantage of this technique is that it can inspect the data in the spectral and spatial dimensions simultaneously. So this is particularly interesting for the case of pyroclastic deposits. What this network does is that it will reduce the dimensionality, and I will not go into detail on the network, but it will reduce the dimensionality from an initial hyperspectral cube to a set of latent dimensions that will be highlighting the main correlations in both spectra and spatial dimensions. So for those of you who are familiar with PCA or PCA maps, this is similar in concept. These latent dimensions are similar in concept to what a PCA does and what a PC map is. But they are different in the sense that they will be inspecting the data also in the spatial dimension. So they will not only extract correlations from the spectra, and also that they can take features that are nonlinear. So what we do is that we have our initial cube, which has this shape. So we have the different images at different channels. And then we will reduce this to 20 latent dimensions, which are related to these pixels. So each of these pixels will be a pixel on the final map. And in the end, with this, we compute a map of the entire planet with the latent dimensions. So there will be 20 maps like this one. And each map will be highlighting different correlations in the data, both from spectra and from spatial. And most of them will look like albedo maps, and others will be highlighting different features that might be interesting for us. So first, we explore what these latent dimensions are doing from a global point of view. And as an example, we have this map, which is a bit different from the typical albedo map that is just highlighting reflectance at a given wavelength, in the sense that here it is clearly highlighting some features that are related to fresh craters and their ejecta. And for example, if we correlate this latent dimension to this map of fresh craters that I highlight in red from Kinzik et al., we can see how it is highlighting pretty well the fresh craters, their ejecta, and also some of the pyroclastic deposits and some hollows, which are fresh features. We have another example of another latent dimension map, which is highlighting something completely different. And in this case, the map is again not correlated with a given wavelength. And if we find correlations in the bibliography, we can see that this map is pretty similar to the map of nanophase iron. Nanophase iron is a product of space weathering. Therefore, although the network is not learning anything about space weathering, it is highlighting some correlations which are similar to what we observe as a result from space weathering. So, but we're interested in the local features in the pyroclastic deposits. So here we can check what the latent dimensions are doing for the pyroclastic deposits. Here we have 5 different deposits as seen with the false color map. And we can look at the dimensions, and we have one particular dimension that is being bright. So it takes these yellow tones, which mean that it's maximized in the areas that are not inside or outside. So they're not correlated with a given wavelength. They are actually highlighting the edge of these deposits. So what we think is that the dimension is highlighting the region where the gradient of properties goes to 0, which means that it is finding with that the edge. And we have another latent dimension, which is not correlated with a given wavelength, and it is clearly highlighting the inside of the deposit from the outside of the deposit, regardless of the background. So knowing that the latent dimensions are an interesting way to explore this data, we now go on to define the extent of the deposits. And for this, we apply a clustering algorithm that clusters the latent dimension into 8 categories, and we obtain these cluster maps. We see that in the deposits, the cluster maps take this very particular structure. It's kind of an onion ring structure where the clusters are going from the vent towards the outside. So we use this as a way to define the extent. We define the inner cluster at the center, and we define the outer cluster at the background material. And with this, we define the extent of the crater. And we can compare it with an example where we have a previous definition of the deposit extent with both MDs and masks data. And this is a pretty circular deposit, so it is good for comparison. And we can see how in this case, we have the definition with MDs in blue. We have the definition with masks with the white circle. And we see how our extent with this cloudy shape, it is matching pretty well the extent from previous works, both in radius and in general location. So we apply this to many deposits, and we can see just briefly some of the examples of the benefits of the algorithm for some of them. So first, we were mentioning that with MDs, we might reach an underestimation, and we can see how in some cases, as here, the data from MDs, the deposit defined with MDs is falling here, and then with masks, we're able to find that the properties actually stand farther away as from initially thought. In the case of Natter Facula, which is the largest deposit on Mercury, we see how different extents, looking with MDs data in red and in blue, they were finding different radius for the deposits. When looking with masks, Barreau et al. 2021, they found a different radius, which was larger, confirming this underestimation. And here we found that the area is going in between the values from Barreau and the values from Thomas. On other cases, we find that our deposit extent matches in radius the previous extents, but in size it is smaller. And this can either be because with masks we find a smaller extent of the deposit, or because we are missing some data, some footprints around here. And this is something that with Bepi Colombo, we hopefully will be able to answer better. And the most interesting use of this technique is for the deposits that are quite irregular, such as these examples. Because using different techniques based on the visual detection, it will produce different radiuses with different focus, and it will not define the extent of the deposits in a consistent way. While here we can clearly define that these originally 5 facula are actually 3. We have 1, 2, and 3 that are combined. And in other cases, such as Lermontov, previous authors were defining them as 2 different circles, and here we have them as a single deposit. And in the case of Orm, we can see again the disparity between different works, and here we match pretty well the extent defined visually. So overall, we have defined the extent of 55 deposits with these techniques, and these deposits contain a total of 110 vents. And out of these deposits, 36 were observed for the first time with this work with masks data, and 17 were observed or were detected with the extent for the first time overall in this work. One of the benefits of this technique that I did not mention is that we can identify the deposits on varying background terrains. So for example, here we have two deposits, Ago and Abeso, that are inside the Caloris planitia, so they are in the high reflectance red plain. And we can see how the previous work was defining a smaller extent, since the brightness compared to the background is not that large, so it's harder to identify them, while here we can define the larger extent of the deposits. Moreover, we have overcome the limitation of overlapping deposits with irregular shapes, and we have overcome the MD's underestimation. However, there are still some deposits where we apply the algorithm and we don't find the extent. And in these cases, we will see something like this for the latent dimension maps, which does not show this onion ring structure that I was mentioning before. And this brings us to the next topic, which is actually to understand why in some deposits we don't find this clear signature. And we ask ourselves if this is something related to the timing. So we have already seen that the deposits are spectrally diverse. And here I just show some more examples going from the very bright Natter facula to some more typically you would see something like this. And then you have deposits that are darker and deposits that directly you do not distinguish from the background with the deep learning. And with deep learning, we further find this behavior. And we see on Mercury that there is a distinct difference between the geologically older units and the younger units. So we see how older units found here are typically darker than younger units, such as fresh craters and hollows. And also they have, younger units have a higher curvature. And by curvature, and I will be talking quite a bit about this from now, curvature, we mean the concavity of this part of the spectra. So you can see how older units are more linear here and younger units are more curved. So we want to understand if this difference between old and young units is also what is happening in our deposits. And for that, we have our collaboration with Dr. Lauren Josbiak and Dr. Erika Jowing. They are geologists that have been looking at the vents from a morphological point of view. So they're trying to understand what is the degradation level of the vents, and this provides an indication of the relative timing of these eruptions. So they classified the vents in categories going from 1 to 4, 1 meaning more degraded, so older, and 4 meaning less degraded, so younger. And you can see already here how between this one and this one, there is a clear distinction. Here you can see the contact between the floor and the wall, and here everything is more eroded. So they provide this classification. And from our side, what we do is that we extract the average and the maximum spectrum from each deposit. So each point here is a deposit. And from the deposits that we outline with the deep learning, and also with in the case where we cannot define it with deep learning, we define a circle of 3 times the band radius. So what I'm showing here is the plot of the spectral properties of the deposits compared to different units of Mercury. We have the average values for Mercury here in the square, and then we have the northern smooth plains, the low reflectance material, impact eject, and hollows. And the first thing that we see if we look at the plot of the visible slope versus the reflectance, we can see how here's the average Mercury, and we see how the deposits are usually brighter and spectrally redder than the average. However, in some cases, it's not the case. In some cases, they are darker and bluer, and there is a very large variability. If we look in the curvature to UV downturn map, and here curvature, when we go towards more negative, towards the left, we are more curved. And when we go towards 0, the spectrum is flatter. We can see how the properties of the older units of Mercury, so the average, the LRM, and the northern smooth plains are grouped here. And we have the fresh craters here and the hollows. So we have the younger features that are differentiated. And we see that our deposits are grouped around the older features, but going towards the values of fresh craters. So again, this is highlighting some correlation with age. So we put the two concepts together. And here we're showing the evolution of spectral properties of the deposits over time, in this case for the reflectance and for the curvature. And what we see, and when we go towards the left, we go towards more degraded, so older deposits, we observe that over time, the deposits become darker and flatter. And also we see that this behavior, this darkening, is initially stronger, And then we obtain a saturation here, and we are stabilized. So we want to understand which kind of mechanisms could create these spectral changes over time. And we propose two different theories. The first theory is that these changes over time are caused by the mixing of the deposit material with the background material underneath through gardening. And for this to happen, it is needed that the gardening depth that we excavate reaches deeper than the depth of the deposit. While we don't have measurements of these for Mercury, they're just estimations, we have also estimations for the moon, and we can compare. And on the moon, over 3 billion years, it is expected a gardening depth of about 5 meters. And for the deposits on Mercury, while we don't have a measurement of the deposit thickness, they're expected to be in the order of tens of meters, so 20 to 50 meters typically. So under these constraints, we don't expect that mixing can reach this underneath layer and cause the spectral changes of the deposits over time, at least not in the central part of the deposit. Another theory is that these spectral changes over time are produced by space weathering. So space weathering, and again, ion irradiation from the solar wind and the micrometeorite bombardment, they are known to produce changes through an accumulation of submicroscopic iron. And over time, these produce a darkening and a flattening of the spectra of the deposits. And again, we don't have constraints for Mercury, specific constraints, but for the moon, from returned Apollo samples and laboratory measurements, it has been found that this accumulation of nanophase iron saturates after 1.1 billion years. And for Mercury, this space weathering could act even faster. So what we obtain for this is that if these spectral changes that we are observing are caused by an accumulation of submicroscopic iron, then this saturation in submicroscopic iron could be causing the saturation in our spectral properties. And this could mean that a part of our explosive volcanic eruptions are actually younger than it was expected. So younger than 1.1 billion years. And to follow up a bit on this, we have some constraints. So here we have two different areas, the Natter Facula, which is the youngest deposit from the morphological and from the spectral evaluation. And we have here 5 deposits in the Hesiod area, which are also classified as very young. And in these cases, we have some information for the composition in the case of Natter. And here we have the nanophase iron abundances as taken from the spectrometer. So these are not compositional measurements, but inferred from the spectrometer. And what we can see is that in the regions where we have a high curvature of the spectra and also higher brightness, we have a lower amount of nanophase iron. So typically, this could mean that the surface has been less exposed to space weathering. It could also mean that the surface is less rich in iron in general, but for the case of Natter, where we do have iron measurements, we see that the surface is actually richer in iron. So the lack of nanophase iron is not associated to a lack of iron. Therefore, from the first constraints, we do see that this theory of a lack of nanophase iron causing the brightness of the deposits is consistent. However, we would need also more measurements from Bepicolombo to also constrain the southern hemisphere and also get more information for nanophase iron abundances. Overall, from our work, what we propose is that the deposits that show a clear spectral signature are actually not as weathered as the others, and therefore they could be forming less than 1 billion years ago in the Kuiperian period. However, we have some remaining unknowns, namely the deposit thickness and the deposit composition, which is something that we will be able to get as new insights from Bepicolombo. However, we have some other unknowns, such as how is the spectra changing with space weathering, with temperature, and with grain size, which is something that we can explore also in the lab. So this brings us to our third and final part of the discussion, which is to understand in the lab how the analogs are measured and how they are affected by different physical and environmental changes. So let's start with the motivation to perform these lab measurements. The first motivation is to characterize an analog that is fresh. And in this case, we want to create an analog that is close in composition to Mercury. So it's poor in iron, rich in magnesium, rich in sulfur. That is also close in physical properties in terms of grain size. So with a very fine grain size. and also to approach the mineralogy. Moreover, on Mercury, we see that there are very large temperature difference both in latitude and in longitude. This is the maximum temperature reached on every part of the surface. So we want to characterize how the analogs are changing after these temperature changes. And finally, as I was mentioning, we use the lab to prepare for Bepi-Colombo. And between Bepi-Colombo and Messenger, there will be very different geometries, both in observation angle and in illumination angle. So as you can see here, Messenger was observing at very high emission angles, while Bepi-Colombo will be mostly observing in nadir conditions. And for the illumination angle, when Messenger was observing at high incidence angles, Bepi-Colombo will observe at low incidence angles and vice versa. Therefore, there is a change in both observation and illumination angle, and this is something that we want to explore in the lab to be able to compare both missions. To do this work, we have our collaboration with Dr. Camille Cartier, who has prepared samples that are very close in terms of composition to Mercury. Here we have the composition in gray of Mercury as measured by XRS by the Messenger mission. And we have the composition of our analogs in the two different campaigns, in blue, the first campaign, and in red, the second campaign. So the objective of the first campaign was to create an analog that was very close in composition. And for that, we mixed several M members, mostly Albright, which is known to be one of the closest analogs to Mercury's surface, with also albite and different sulfides in the end to create this mix that approaches as possible Mercury's composition. On the second campaign, we focus on a variability in composition. As you can see here, with the red samples going through the composition in magnesium, in aluminum, and also in iron. And for that, we create 3 different samples with different compositions, mixing Albright, in one case with olivine and sulfides, and in the other case with albite and sulfides. And we also focus on the grain size variability. So we create each of the compositions with 3 different grain sizes, and you can see here how we go from very small grain sizes, less than 25 microns, which are similar to Mercury's regolith, to larger grain sizes up to 250 microns, which are comparable with the size for the pyroclastic deposits of Mercury, as is thought from photometric analysis. We do this analysis at the DLR lab. They have a planetary surface spectroscopy lab where we can measure bidirectional reflectance with the Bruker vertex. You can see here the spectrometer. And behind, you might not see it very well, but here there is the heating chamber. And with this, we perform three cycles of heating up to a maximum temperature of 450 degrees, which is the maximum temperature on Mercury's surface. And as you can see here, this is the sample inside the sample compartment. You can see these 2 different motors. These are actually to activate these 2 arms, which allow to change the observation geometry. So we can change in a same plane the incidence and the emission angle. And we perform some additional measurements here at LIRA to support the calibration. So let's go with the results. And here I show the Mercury mix from the first laboratory campaign and the 3 main end members. And if we want to characterize it and compare it with Mercury, the first thing that we see is that it has a red spectral slope, as we would expect, and similar to Mercury. And this slope is lost in the near infrared, which is something that we don't see on the average Mercury spectra. Moreover, we have a curved shape in the visible and a downturn in the UV, which is something that reminds us more of the spectra of the fresh units that I was showing, of the hollows and the fresh craters, than the average Mercury spectra. As I showed before the composition, we have an iron abundance that resembles that of Mercury. And with that same iron abundance, we can still see the faint, but we can still see the iron band here at 900 nanometers. And for the albite, we also see some minor hydration bands. And finally, for the Norton County dark end member of our sample, we see that it's actually dark, it is flat, and in this case, we don't observe any of these absorption features. And overall, we see that for each sample, we have different measurements depending on the incidence and emission angles where we measure. So we want to characterize what are the changes with observation geometry. So for that, here on top, you can see how we performed 6 different measurements at different incidence and emission angles, but we want to explore them separately. So we have our changes in incidence going from 30 to 60 degrees, and from emission going from 20 to 40 degrees. And we can look at them all together in these phase angle plots, because in this case, the phase is the sum of incidence and emission. So the first thing that we observe is that for our mercury mix analog and DM members, the samples are darkening with increasing phase angle, and this is both caused by a change in incidence and a change in emission. Regarding the slope in the visible, we can see that the samples are reddening, but this behavior is mostly due to the change in incidence angle. So we see that in this case, incidence is dominating our phase reddening. And regarding the shape of the spectra and the curvature, we observe a strong flattening. So just for reference, 0 here means that the spectra is flat. And we see that this flattening is stronger with emission angle. So we observe that emission is a very important parameter to understand the shape of the spectrum. Here we have our results from our second laboratory campaign, where we perform changes in composition and in grain size. So we have the 3 colors related to the 3 compositions shown here. You can see how the blue is the closest one to mercury, and also the red is higher in iron, in the higher end of the iron abundance. So first, we see that, of course, with more iron, our absorption band is stronger. And when we go towards lower grain sizes, when we decrease the grain size, we observe a brightening of our samples and also a very strong reduction of the absorption bands. And this strong reduction is particularly important for the samples with more iron. And if we focus on the analog that is closer to mercury overall, so closer in composition, closer in iron abundance, and also closer in grain size, which is the blue spectra with the finely dotted line, we observe how our band is almost gone. So while we observe the band when we look at them with 125 to 250 microns, in this case, our band is almost gone. So with this, we conclude that grain size is a very strong contributor to the lack of absorption features on mercury, besides the lack of iron in general. And finally, in the first campaign, we had an extra bonus since we were able to heat the samples and observe the effect of heating. And in this case, we see that after heating, there is a very strong brightening of the samples. Also a very important reddening, as if you look at the slope in the visible, we observe that after heating, it increases. And most importantly for us, a strong flattening. So if you look at the shape, we see that here, the fresh spectra has the curved part in the visible, and here it becomes flatter. And finally, we observe that different samples will receive a different effect. And as we observe, the reddening actually is correlated with the magnesium abundance, with more reddening for samples with more magnesium. So finally, if we look at these samples before and after heating, we can compare them to mercury, since this was the objective from the beginning. And we were surprised at the beginning to see that our spectra that was trying to match the average mercury, so we were not trying to replicate specifically hollows or fresh craters, but it was not being close to the fresh mercury as to the average mercury spectra, but it was close in shape, and take into account that these values are scaled for reference, but it was closer in shape to the values for hollows or fresh craters. So in general, to fresh units. Of course, since our sample here was fresh, it made sense that our spectra is closer to fresh units. And after heating, when we heat the samples, we see that the spectra in shape, it becomes flatter, so closer to the average mercury, also redder, closer to the average mercury. And also we see that the point where the slope becomes more horizontal, it moves from here to here, which again brings us closer to our slope in the near infrared. So overall, we observe that after heating, our spectra becomes closer in shape to the mercury average. And what we extract from this is that while composition, of course, plays an important role for the spectral signature of fresh units on mercury, the effects of space environment are strongly flattening and erasing the features over time. So this is the end, the conclusion of my presentation. And this was actually something that my supervisors asked me to do at the first year, after the first year of the PhD, where I was a bit lost. So you can see how at that point, my research was quite a mess. And luckily, nowadays, I can provide a bit of a more structured summary for the conclusion. So I will go through it. First, we have adapted a deep learning algorithm to explore the data from the messenger masks instrument. This has highlighting the importance of using a three-dimensional technique to explore in particular pyroclastic deposits. And with this, we have extracted the shape of 55 deposits containing 110 vents. Of course, this provided extra questions and also inputs to explore the timing of these eruptions. And we performed an integrated spectral and morphological study of pyroclastic deposits. With this, we have found that over time, the spectra of the deposits is darkening and becoming flatter. And this suggests that the pyroclastic deposits are forming more recently in the history of Mercury. And again, this still provided some inputs for Bepicolombo, but also some extra questions that we were able to explore in the lab. And in the lab, we characterized the Mercury analog under different physical and environmental conditions. And we found that the spectra is flattening with heating, which is interesting to explore the conditions of Mercury. We have characterized the effects of incidence and emission angles. And we have found also that there is a very significant decrease in band depth with decreasing the grain size. Finally, this work has been possible thanks to many collaborations, and these collaborations are ongoing and going into some perspective works. So I have an ongoing collaboration with Dr. Erika Joing and Dr. Lauren Josbiak on continuing to look at the timing of these eruptions, and in particular, looking at whether these eruptions can be stopped and then restarted. So if there is an interrupted timing in some locations. We continue also the collaboration with Dr. Sébastien Bes and Dr. Océane Barrault with the eruption modes, looking at whether some of the eruptions are caused with single pulse volcanism and others with more prolonged eruptions in time. Also with the lab, we continue the collaboration since we have found this link with magnesium. So we want to understand if with localized photometric studies, this would increase the understanding of units of mercury with different magnesium abundances. And finally, I continue my collaboration with Dr. Emma Caminiti on looking on the lab at how the photometric properties of different analogs are changing before and after irradiation, and how we can obtain more information with off-pointing of Bepicolombo to understand space weathering. And finally, I have been mentioning Bepicolombo, and I wanted to highlight some of the contributions that this work has done for the mission. So we have demonstrated a use of a deep learning algorithm to process hyperspectral images. And this can be particularly interesting as a precursor for the symbiosis instrument, which is found here, which is a hyperspectral imager on Bepicolombo. Moreover, we have provided targets of interest to continue study the eruption timing, and in particular to study the thickness of the deposits with the laser altimeter, the pyroclast size, and the spectral signature with the symbiosis and MERTIS spectrometers, the composition with MIX and MGNS, and the precipitation of ions on the surface with Serena MIPA. And finally, this idea of bridging the gap with messenger through off-pointing, we have provided it as an input for the Young Scientist Study Group suggestions for a mission extension. And this is my last slide, and I just wanted to show it as a way to thank my supervisors and the OSIP program for the opportunity to have visited all of these places during my PhD. I have gone to 7 conferences in different in different countries. Also to the 3 different Bepicolombo WTs, which have really helped me to become very involved with the mission, which is something that I have loved. The different symbiosis team meetings, the laboratory campaigns at DLR, and also the opportunity to have gone to the summer school in Albach in Austria to explore a completely different topic, exoplanets, which was then followed up with a concurrent design facility study at an ESA facility in Belgium. And of course, I would like to thank the OSIP program and the people at ESAC for welcoming during my 5 research stays at ESAC, and the opportunity to have been teaching and performing outreach here at the Paris Observatory. And this will be all for me, 47 minutes. So thank you, and I will be happy to answer any questions now.
Thank you, Mireia. Maybe, yes. Can you put your slide up again? Who knows? There it is. Okay, so we can start the question sessions. Nancy, would you like to start, please?
Yes, happy to. Congratulations on a really impressive work here for the overall thesis. I really appreciated the combining of the remote sensing data with the experimental studies to try to get this holistic approach of understanding the surface of Mercury. I guess I wanted to start with the experimental ones because in some ways it's kind of sad that like the spectra depends on so many things, right? It depends on the grain size and the temperature and the viewing geometry. How do you think when we get the data, that we'll use all of that in order to do that? Do we really just need a giant library that covers this whole space? Or, how do you see this complicated interpretation getting applied to the Bepi-Colombo data, for example?
Yeah, thank you, Nancy. So this is actually a very interesting question because it's true that there are several factors affecting in particular the depth of the bands, which is something that if we aim to observe any bands on any units, I don't know if, okay, I think you're hearing me. Yeah, okay.
Yeah, I'm hearing you.
Okay, good. Because I see the delay in the in the video. Yes, sorry. So there are many factors. We have seen that grain size could be particularly reducing the band depth. Also, the presence of dark faces on the surface. Also, the observation geometry. So I think that first it is very important to get complete coverage of different units on the surface. So in particular, with the observation angles, and we have highlighted the importance of the emission angle in particular, which Bepi-Colombo will be observing mostly in nadir conditions. So this is something that we are highlighting. If it would be very good to observe with off-pointing to have a larger database of observation angles, and also to observe different units that might have different grain sizes. And of course, to perform this larger library of observations with observation geometries, also for different terrains. And in particular, we have highlighting the importance of magnesium. So if we could get these off-pointings for different geometries, for different magnesium terrains would be very nice.
So can you do that? I mean, I know on Messenger, we had a few specific targets, actually, like they were treated like science targets, where we took specific parts of the planet under varying different conditions in order to get the photometric correction. So even though like the majority of Bepi-Colombo's prime mission will have one pointing, is there a possibility to put in a target over the high magnesium region or some other, choose whatever you think is the most appropriate to build that up in one location, which would enable it to be applied planet-wide? Or do you think you have to wait until like the extended mission where the pointing options are more open?
Yeah, so I think for now, during the nominal mission is still complicated. It's something that we proposed with Sebastian in the last symbiosis team meeting to see whether it was possible and it was well received by the community to perform this off-pointing. In the nominal mission, there are several constraints, so it is still not known if this off-pointing campaign, let's say, or photometric campaign will be possible. But this is something that for the extended mission, and for me, what I can do for now, it has been as part of the young scientists, but we have proposed this idea of performing off-pointing in different geochemical terrains to complete this coverage. But I think it will give, for now, it looks like it's going more in the extended mission.
Yeah, that makes sense. It might be, I mean, I know it's still ongoing, but it does seem like a few targets, especially since you've shown it's so complicated. If there's just a few opportunities for at least over a few targets to get there. So what sort of laboratory work then do you have planned follow-up? I know this is kind of a sampling of the space, but what do you think are the most important next steps for the laboratory aspects?
Yeah, so for now we have conducted the heating, and I think that of course on Mercury we have different effects cumulatively working on the sample. So we have the heating, but also the effect of space weathering, and I think this is the step to go forward. So for now we have characterized heating, and with this collaboration with the EMA community, we will continue to explore also the effect of ion irradiation. And the idea would be to bring cumulative work, so to have a sample that has been first heated, then irradiated, then perform different cycles of heating, and in this way to understand the cumulative aspects of all of these processes that are affecting mercury.
And I don't want to hog the questions. Should I be quiet for now and let somebody else ask some questions, or do you want me to ask more questions?
Thank you, Nancy.
If you can carry on if you want. Usually
okay.
It's the way we do it. Yeah, please do.
Oh, is it? Okay, perfect. Sure. So then relating to the temporal change that you see for the pyroclastic features, I thought that was really intriguing. I guess kind of the limitation there is just the messenger data that's only good over like the northern hemisphere, and the southern hemisphere is not as useful. Or what's the main limitation in the data, and how is Bepi-Colombo going to advance that?
So for the spectral data, the issue with the southern hemisphere was more in terms of the separation of the footprints of the tracks. So it's true that it was limiting the amount of targets that we could measure. So out of the 250 deposits that there was only around 150 that we had enough data to measure with the deep learning. So this already is something that Bepi-Colombo will be able to extend this catalog of deposits. And then of course, so I'm talking with masks. In the case of masks, we are limited in the spatial resolution. And then of course we have the MDIS images that have been a very useful way to explore the deposit so far, but they were more limited in the spectral domain. And the benefit is that Bepi-Colombo, of course, it will have symbiosis, which is resolved spatially and spectrally. So in this way, we will provide more coverage of the deposits and also at a higher resolution. So in this sense, if we would apply exactly the same technique to the data from symbiosis, we should be able to get a higher amount of deposits and also refine refine this extent that we have defined.
And since like a lot of the southern hemisphere terrain like seems kind of old and cratered, do you expect the pyroclastic features down there to trend with that as well, that their spectral properties might be more similar to an older terrain, or do the pyroclastic features not correlate with the overall terrain? They're just younger overall.
So we performed some analysis to understand if there were correlations with latitude and longitude, because both the terrain could be older, but also there are differences in the amounts of weathering rates of ion precipitation and bombardment in latitudes. And we didn't find any correlations, because we would be expecting that maybe this, I can maybe point to the slide, this dispersion that we see in our plots. So the fact that it still has some vertical dispersion, we thought that it might be related to these changes in location on the planet, but we didn't find any correlations. If these eruptions are actually happening after the terrain was emplaced, then we could be expecting that there are no changes, but of course the weathering rates are different, so we could expect some changes. So when we get the data and we have a higher, longer catalog of deposits, then hopefully we will be able to explore this in more detail. Also here we are missing the compositional information, which in this case composition will be very helpful in further understanding this variability between deposits that we observe.
Yeah, no, that makes sense. The compositional information will be really key as well at a scale that's useful for this study. So going to the machine learning where you started with originally, I mean, I was just so impressed that you could like get things out of that mask data set from this approach, and then see that the deposits extended so much further than sometimes we saw in the imagery, and really to define sort of a boundary there. How much do you need to let the data for Bepi-Colombo like build up to have a complete data set before you can do the machine learning on it? Is it the sort of thing where you have to kind of wait until you have like 1 year of data, or can you kind of do it as you go? Like how big does the data set have to get before the machine learning is a viable approach?
So the machine learning, here I showed it as a global map, but in reality we are training it with individual images. So in the end, we get with this global map, but we train it with the individual 5x5 pixel images in this case. So once we start getting data, of course, the deep learning in this case, we're training with 50,000 of these images. So once we start, but take into account that they are sub patches of larger images. So let's say that once we start getting data, once we reach a significant amount, we can already start training the algorithm. And of course, if in the first 6 months, there is the plan to have a global map of the planet with Symbiosis, then after these first 6 months, when we have the global map, we can train the algorithm with the entire database and then recheck for the results. But then again, in this case, I applied it for pyroclastic deposits, but this could be used also to detect hollows or to explore other features like craters. So the limitations of the deep learning in this case were more related to the spatial availability of the footprints, but once we have that covered, we will be able to go farther.
Yeah, no, I mean, and you're probably aware of Ariel Deutsch's work kind of applying sort of an approach for the hollows. I mean, how does this compare and contrast with that? I guess hers was more morphology than spectral, right?
Yeah, so the work from Ariel, it's very interesting, and it's quite similar to in concept to what Lauren and Erica were doing visually. So to understand more from the morphological point of view, this degradation and the old age. So I think they could actually combine pretty well to have from one hand, because it's two different aspects, right? We have from one hand the morphological degradation aspect, which you can get from images, and then you have the spectral degradation, if we can say it in that way, aspect which we can get from the spectra. So this is something that would be very interesting to look together. So to look at or to even train a network for morphology and then a different one for spectra.
Yeah, exciting. Yeah, well, I think we're all looking forward to Bepi Colombo, and this is really important work to help motivate that and to help inform some of the targets even, and test your hypothesis about these pyroclastics being quite young. So anyways, I have no more questions. I will pass the floor over. Thank you very much.
Thanks, Nancy.
Thank you very much, Nancy. So we'll go to the next reviewer, Patrick.
Okay, hi. Do you hear me well, including Nancy?
I can, yes. Hello.
Okay, thank you. So I will follow on, and first of all, I will express, my congratulations to you and to your supervising team. To put it very bluntly and in a very straightforward way, I would say it's a hell of a good work. Now, of course, these are the compliments, but the game is to ask you some questions. And I will go into some observations and maybe remarks. And first of all, Nancy has touched on many points, so I may not be developing as much as she did. But my first point is maybe about when you go to the machine learning process. I'm very pleased to see what you've done with this work and this approach. And personally, I've been advocating for many, many years beyond Mercury observation and about hyperspectral work. I did recommend that we should use a combination of spectral and spatial observations to go further with the outputs that we can get from hyperspectral data. And what you do here makes me very happy to see that there are very positive aspects that can be used here. However, I'm still a little, let's say, frustrated, if I may say, because I didn't get a full understanding from the written report. And today, again, with a oral presentation about what is the benefit with your machine learning process on the spectral side. I know that the spectra are very difficult spectra for Mercury. They're featureless. We mainly play with the slope and so on. But could you develop and elaborate a bit more about what is the gain that you made on the spectral side with your machine learning approach?
Yes, and I was thinking that you would make this question based on your report, so I prepared a bit. So it's true that I have been mostly showing these kind of latent dimension maps, which directly, if you look at them like this, they're not telling you anything about the spectra, although they are doing in some way. So what I did, and I didn't publish this because in the end it was not that much related to the work, but what I did was to try to correlate what each of these latent dimensions were extracting from the spectral data. So first, this we do have it on the paper. It is a correlation of each of the latent dimensions with different spectral channels. So just looking at whether we are highlighting a given reflectance or if we are highlighting a given feature. And we found that around 15 of the latent dimensions were correlated, of course, with spectra. And these 5 or 6 that are highlighted were correlated to 96%. And then we had some other latent dimensions that were correlated with different spectral parameters that we know. So for example, with curvature, with UV slope, with different parameters. But the idea is that since the deep learning, we use it as an exploratory technique. So of course, if we see that it is extracting the information from the slopes, we would expect it. Again, we don't have absorption bands, so it's hard for it to extract relevant features. But what we did and what you're seeing in these 3 plots was to take each of the latent dimensions and to apply the algorithm in the reverse way. So we would feed the latent dimensions at the beginning, at the middle of the encoder, and then we would decode it. So we would feed what like the latent dimension set to 0 or set to 1, and then we would see which spectra it was extracting. And then with this, we were able to see how some of the latent dimensions were governed by the changes in brightness only in the visible part, or the changes in brightness and the slope in the visible and in the near infrared, or some of them, as the one on the top, it was not so much governed by the changes in spectra itself, only a little bit, if you will, the slope in the near infrared. So this was our way to understand what it was doing. But of course, the downside of the deep learning is that it is very complex, so it extracts very complex correlations, so it is hard to understand exactly where the correlation is coming from. So it is hard to extract a new spectral parameter from this. So I think there are ways to go forward with this and to use the autoencoder to tell you also more information about the spectra. In our case, we didn't do it as much because with the spectra of mercury, they are very flat, and even the pyroclastic deposits that still show a bit of curvature, the differences among them are still very limited. But I think for other bodies, Mars or bodies where you do actually have some visible features, it's a very, very nice technique to explore both spatial but also the spectral dimensions.
Yeah. Okay, yeah, thank you. But I think there is a real bonus to use your approach, no doubt. But I was still kind of intrigued, if I may say, because I know these spectra are kind of bland, very featureless. It's difficult to extract a signal. And because of these featureless aspects, conversely, I mean, how sensitive maybe is your machine learning approach to technical potential defects that you could have depending on the sensors? And this, of course, has to do with what you used here as a data set, but in the future with potentially maybe some technical little glitches that we may have between the sensors on board Bepi Colombo. Do you have a view on this? Could you say something?
So deep learning is also used to remove noise.
Yeah.
And here and again, I was focusing more on the spatial. So here you can see how it goes from the initial reflectance, which is very noisy because we have the measurements that are interpolated, but still very noisy, and then to reconstruct what the latent dimension is doing. This is a way to remove noise in the spatial dimension, but in the same way, it can remove noise in the spectral. And they have been doing this for Mars, I believe, not with the same algorithm, but with similar ones. And yeah, it's a way to denoise the spectra. So it is not an issue. It is actually something that deep learning can also help to achieve, to remove this noise between, or these artifacts between channels. And actually, in our spectra, there is this small gap between, all the spectra have this small gap that is not linked to the mismatch between channels, but it's something that they always ask about when you present the spectra from messenger masks. And actually, it's something we were expecting that the algorithm would be busy with this gap and it would find an error there, but it actually didn't present any issues for that. So we think that the algorithm can easily find what is noise, and if you decide to keep it, perfect. And if you treat it as a feature of your spectra, you keep it. And if it finds that it's noise and it's something that it's consistent, then it will remove it.
Okay, thank you. Still, it's a bit connected to this. Let me ask you maybe a little bit cheeky question, but did you use separately your machine learning approach? And did you train it independently, or you had already a view at the Venn degradation classification produced by Josniak when you train your machine learning system?
It was completely independent. So our
Sure,
work
really?
completely 100%. And I was, when I saw the plot after Lauren provided the results, we were extremely happy because once I did the training, I did not touch that again. I have not touched that code for 2 years. And we saw that it worked. And I think it was a very good day in my PhD because so yeah, it was completely, and the objective, so this work actually, I didn't mention it, but it was part of a NASA proposal that Sebastian together with Lauren, they created. And when I started the PhD, I was kind of tasked within this proposal. And the idea was to do it independently and to go even farther, so that now that we have, and we found it already quite quickly, but the idea was to see if these events that don't have any signature, they actually didn't have any signature. So it was already in the task to be independent. And then since the collaboration is with people that are far away and very busy, and hopefully seeing this, but very busy with their job, this was a one-time checkout process. So yes.
Yeah, anyway, because anyway, afterwards, it's a great result. It's no doubt. But however, one point is, could you go back? I forgot the slide, maybe slide 20 or so. There was one example with what you call the GEDES or GEDES crater. Is that this one or the one before? Yeah. How do you pronounce it? GEDES? GEDES? Whatever. Okay, could you comment a bit more here why you have kind of such a difference or discrepancy between the extent defined by your work and what was previously proposed for this one?
Yes. So for this, I think I have to go to, what is happening? Well, it's not going, okay. So since we are not using the data from a hyperspectral imager, but from a point spectrometer, in some cases we have something which is very well covered, like in the bottom, and in some cases we have something that is very poorly covered, like on the top. When it is, thank you.
Thank you.
So when it is more poorly covered, like here, what we do is that we define a quality parameter and we remove these footprints, and then we don't use, so this, for example, we wouldn't use it. However, even in the cases, this is a very good case, okay? So even in the cases where we have something that it is not so well covered, we might have some small parts that are missing. So for example, here we can still see the initial spectral signature, but there are some parts that are missing. And as a result, even if we try to maximize our quality, but in order to still get a good amount of deposits, in some cases we have some gaps. And in this case, we don't know if the lack or if the mismatch is due to this gap, due to the fact that we don't have enough data, or this is actually because the algorithm is finding that the deposit is linked to other properties and finds this direction. So hopefully with BepiColombo, we will have the full images and we can treat everything together.
If you have to gamble, what would you propose? What do you expect with BepiColombo?
I expect that BepiColombo will show something quite different. I actually expect, and here my supervisor won't like to hear, but I expect to see some absorption bands with BepiColombo in some cases. Not in, maybe in Nater, maybe in some of the deposits, because as we have seen with the lab, okay, the iron abundance is very small. Also, the grain size is very fine, although with the deposits, it might be larger, so it might be a good target to try to see these bands. But the observation geometry of Messenger was, it had very large emission angles, and also it had very large phase angles. So with this geometry, already the identification of absorption bands was more difficult. And also the footprints were larger. So maybe if we are able to go through Natter with smaller footprints and with nadir pointing geometry, then we might see different things to what we see with Messenger.
Okay. Okay. Well, now there are a few more questions. If okay, it's first of all is on your lab work aspects. Again, it's a beautiful piece of work, and I think that all the darkening, reddening, flattening aspects that you have been documented have been known for ages about as a function of observation angles and grain size composition, less about the heating effects. And this is nice that you also address this. However, given what we're going to discuss about the geology afterwards, the missing part, in my opinion, of course, is the space weathering aspects. Since you said it very well, and in the future, I hope you can continue in this direction, but very likely the space weathering effects at Mercury are going to be certainly prevailing in many aspects about what we see here. And it's a puzzle for me that you didn't touch it so much in your PhD. So I know you cannot do everything, but do you have maybe a more elaborated answer to provide to me? Why so?
So in my PhD, we were two colleagues at the same time. One is present here, and we were kind of doing a bit of parallel work. So I was attacking the aspect of the geometry of observation and the heating, which is true that the geometry of observation has been seen, but not for a Mercury analog. So here we wanted to characterize the values and to try to compare with MESSENGER. And of course, the ion irradiation is a very interesting aspect, and they do it here in Paris, they do it at EIS. We didn't have time to do it with our sample, although our sample has been irradiated. So the mercury mix that you see, it has been irradiated at EIS, and we are following up also in this collaboration with Emma to try to measure it after irradiation. It's not the sample that has been heated, so for now we are separating the effects. And it is true that it will likely dominate because, for example, we have seen a brightening in the lab, and in Mercury, what it is known is that with space weathering, there is a darkening, but the effect of temperature, it has found that instead of producing this nanophase iron particle, it would produce a slightly larger submicroscopic iron. So instead of being smaller than 40 nanometers, it would be larger. And therefore, what this produces is that you still darken the terrain, but in this case, you don't redden it. And this might be also linked to the cumulative effect of the temperature and the irradiation. So it is true, it is something that it would have been nice to do this as well in my PhD, but it's something that we are continuing to do after the PhD in this case.
Okay, yes, but I mean, just scientifically speaking, I think it's really valuable to go in this direction and to do more, because you're certainly touching something which is critical to understand the surface of Mercury. So, and along with this, anyway, you wrote it also in your PhD somewhere, but I would like you to comment a bit more about something which appears to be, to me, as very central with regard to this matter is how will you test the hypothesis that the spectrally older deposits are saturated in submicroscopic iron in the vents and the vicinity and the nearby deposits with Bepi-Colombo? What is your idea to define these targets, first of all, and what is the strategy behind, according to you?
So for now, submicroscopic iron is tested with radiative transfer models. This is a work that was done by David Trang with MESSENGER data. So with Bepi-Colombo, the good part is that we can target observations with a much higher spatial resolution. So in this case, and we're already providing us to Symbiosis the target list, and almost all of the deposits are for now part of the target list for the dedicated observations of Bepi-Colombo. So at least this is something that we don't have to worry about. But what I think would be nice is to also define observations with different geometries and to be able to refine these radiative transfer models. And yes, as we said, we need the composition or we need the nanophase iron. We also need the composition to be able to understand the link between the nanophase iron and the original iron. And we also need the background. So we cannot just observe the deposit, because if we just observe the deposit, we don't know how that measures compared to the terrain. As Nancy was saying, the southern hemisphere, it's older. We have to compare it with the terrain that is around it. So I think in that case, and this is actually a very good point, because that means that in the target definition, we have to also include the background, which is something that for now it's maybe not happening.
Yes.
So this raises a very good point for the operations of Bepi Colombo, yes.
And I think this is likely going to be a very critical and important point to be touched on. And anyway, again, what I like very much is from your lab work is the development, maybe that's not directly you in your PhD, but the development of your mercury analog is a very valuable thing, which is extremely useful now. And maybe, since I have maybe to close my questions, it's not a question, but my last point is, anyway, I enjoyed very much your slide by the end of your presentations when you speak about the messy aspect of your subject. And I think you try to put some good order in some of the key questions which are, arising. And I think you did very well, especially having a supervisor like Sébastien Besse, who is, the master of the MESS database. And so you try to help him. But thank you. Okay,
thank you very much.
Thank you, Patrick. We carry on with the question session. Kathleen?
Hi, Mireia. First of all, congratulations. So 10 years ago, I was here standing on this stage, and I also had to deal with both what we're doing at Lesia, it was not yet Lear, and what we're doing in the lab. And I know how difficult it can be to reach the two worlds. So very nice job doing that. And I was also very impressed with this deep learning stuff that you added to the work. So it's not 2, but 3 different work you've been doing here. And that's really impressive. So you can really be proud of you. I have a few questions. So you know that we met 2 years ago in Lapland. It was the very first time I was attending a conference on mercury. And a question came to me when I was reading your PhD thesis. Do you think that the spectrum we have on mercury from the messenger data is, let's say, blurred due to the extreme geometric conditions of messenger? And considering your lab work showing that grain size, viewing geometry, and so on, that showing you're doing lots of stuff on the spectra. So flattening, decreasing the band depths, and so on. So is it the real spectrum we have on mercury from the messenger data? And do you expect something else to maybe? So you already a bit answered this earlier, but this is really something that questioned me when I was reading the PhD. So what would you say on that?
Yeah, so I don't want to bring down the messenger data because I think it's really, really valuable data. But of course, the observation geometry was very extreme. It had very large incidence and emission angles and globally very large phase angles. And it's true that from our lab, what we have seen is that this would mean that the spectra, most importantly, they will change in shape, because the change in spectra in the end, in reflectance, in the end, this is something that is photometrically corrected. And actually the messenger team for masks, they corrected for the reflectance, but they did not apply a wavelength dependent correction. So everything is scaled up or down, but not changed in shape. So I think that for the reflectance, we might see that that mercury is actually a bit brighter than it was, depending on the calibration, but this is not that different. But of course, the shape is something that might change. And in particular, the shape of the curved part, so of the UV and the start of the visible. Unfortunately, with symbiosis, we don't get to 300 nanometer, we only get to 400. Still, we might see a bit this start of the curvature and to change. So this is also why we wanted to do these measurements, because we want to compare this UV part, which has been to see, which is very important to see this UV downturn, this curvature. But yes, so I think that it's not that they are blurred, but they are a bit, they will be a bit different, in particular in that UV part, visible part.
And how important do you think it would be to maybe acquire data with symbiosis and with the same geometric condition than messenger? So we have been talking a lot about half pointing with Sébastien for different reasons, but what about comparing the two data sets, at least for one specific feature we do see on the surface? So how important do you think it would be that we push the team to this direction?
I think this is extremely important. So first, to be able to compare this missing part of the spectra, this is something crucial, but also, and this is something that we were also proposing to this young scientist study group proposal for mission extension. So if we want to compare images from features with messenger, and in particular, if we want to see changes, so there is this idea that hollows might be still actively forming. If we want to check if something changed from Mariner 10, because even if though they were not discovered with Mariner 10, they are visible. We checked on some of the hollows. You can see them with Mariner 10 images, to then messenger, and to then Bepi-Colombo. It is very important to have them with the same geometry. And we were seeing some of these hollows between Mariner 10 and messenger, and you can't really tell if there have been changes or not because of this difference in viewing angles. So I think it would be very interesting to take, I know of pointing is very difficult for Bepi. So I think if we can select a few of these fresher hollows that the work from Ariel Dauch has found that they are fresh. So if we could select a couple of these fresh hollows that are the most potentially changing, actively changing nowadays, and we look at them with the same geometry that messenger looked at them, I think it would be extremely beneficial. But for that, we have to be lucky both in incidence, so we have to be able to measure with the same illumination for the sun, and then to be able to perform off pointing at that moment. So maybe for the extended mission.
Okay. Maybe just some interrogation concerning your deep learning algorithm. Did you specifically train it to look at the pyroclastic features, or was it like a more general search on the whole surface?
So I trained it originally with the already discovered pyroclastic deposits, and I took an extra area so that it already covered the background material. And then just for fun, because then this worked, so I worked with this, and then just for fun, I reapplied the training to the entire planet to compare with the work that Emma was doing at that moment. And we found very similar extents of the deposit. I think that already by including the pyroclasts and the background, it was able to identify them from the background.
Okay, I'm asking this question because I'm wondering, you know, in the 20 latent space dimension that you showed, so you've been showing like the UV downturn, you've been showing the nanophase iron particle. So I was wondering how many more information there are existing right now in your data that maybe you left apart to focus only on the pyroclastic, because I'm really interested how much your algorithm with only be trained on the pyroclastic was also finding other features. And so I'm wondering if you plan to do something with the extra data, or what's going on with those.
Yeah, I think it would be very interesting to apply it to features like hollows, because I'm in this data set there are already hollows, and the problem is that they are so small compared to our spatial resolution that they're just 1 pixel or a couple of pixels. But yeah, I think it would be very interesting to take another look at the data, and specifically when we have higher spatial resolution with Bepi-Colombo, and look at other kinds of features, because of course here I focused on just one thing, but for crater rays, for hollows, and for many of these features that have some specific spectra, or LRM, for example, it is something that could also be looked with this. And I think it's, and for sure, I think if I looked more into detail on the latent dimensions to try to find these things, I think they are there, but
Okay. Question about the space weathering. So, you know, this is what I'm doing every day. I'm wondering what is the influence of the iron on all what you showed, and also you mentioned the nanophase iron, the submicrometric particles, but how can we conclude on the space weathering due to iron, like what we know on the moon, when you start with a material on Mercury that is less rich in iron? So can we really expect the same space weathering effects? And can we conclude so strongly on the iron importance on these features?
No, so recently there are some works looking at the effect of carbon in this case as the darkening agent. And here we have focused on iron, of course, with analogy on the moon, and also because very small amounts of iron, like 0.5% weight of submicroscopic iron can already produce changes. But of course, if we have only 1.5% of iron, this means that a very large part of iron has turned into submicroscopic. From the estimates from the radiative transfer models, they find these abundances. They find a 1% abundance of nanophase iron, but of course, this is based on modeling on the spectra. So of course, this is not definite, and I think that including other sources such as nanophase carbon, it is very relevant. And there are laboratory works very interesting from Autumn Shackelford in the US, and they have been looking at incorporating incorporating carbon in different in graphite form and carbon black to different samples, to olivine and enstatite, I think, as well. And then they incorporate it to the sample. They already see the strong reduction of the absorption bands, and then they apply, in this case, lasering to simulate micrometeoroid bombardment. And again, they see again the reduction of the curvature and of the brightness. So they see, and also a reddening. So the effect of these other darkening particles is very similar, but it is true that here I've been mentioning iron because up to now, up to very recently, it was the main particle in the game, but I think that other particles, and in particular carbon, are going to be very important, yes.
Okay, good. Can you go to your slide 40? Yes, so I was a bit surprised on this plot, so I had to go back to the thesis, and then I realized that you have the second scale. But because before you explained that when you were doing the heating, you were brightening the sample, and here you see the reverse thing, but we have different scale bar on the reflectance. And so just to make sure, here your discussion is only on the shape, and you completely exclude the level of reflectance. But why? And how we can conceal the two.
Yeah, so here I was focusing on the shape because it's true that it was the thing that surprised us the most. So originally the samples are already brighter than mercury, so we were not comparing reflectances. And the shape of the original analog, the fresh analog, was surprising us for this curvature. And then when we look at the shape of the heated one, we see the flattening and we see the extending into the near infrared, which is very interesting. But of course, we have also the brightening effect. And there have been very few studies on temperature, and there have been some of them for mercury, both for olivine and for sulfides. And what they found is that there was no consistency between brightening or darkening. There was some correlation with the magnesium. So the samples, for example, magnesium sulfide, it would brighten, and calcium sulfide, it would darken. And again, for the olivines, the same. When you had them in powder form, like in fine grain and not in a pellet, they would brighten. So we see that this brightening effect, yes, we have observed a brightening, but maybe if we observe the sample in a pellet form, it will darken. So we have to be very careful when we discuss this brightening. And this is why in this case, we focused on the shape, because these were the effects that were better helping us to understand what is happening on Mercury's surface.
Okay. And a final question, because you went to Berlin to acquire the spectra, did you benefit from using the mid-infrared spectrometer?
Yes. We measured them in the mid-infrared.
Perfect.
And this work was part of a collaboration, and there was they gave us something extra, which was this heating, and we gave them the mid-infrared measurements because we were focusing on the visible part. But these measurements have been done. Perfect. I'm not fully aware if they have been analyzed. They have not been published. So this is something that if you're interested by, we can discuss further.
Sure, yes. Sure. Okay, thank you very much.
Thank you, Kathleen. Fabrice?
Thank you very much. So thank you very much for the invitation. And yeah, I mean, I join the other voices to say congratulations. The work is very impressive for me as well, because I'm not really a geologist. I'm coming from another direction. So I learned a lot reading your PhD. I would, I mean, there are a few questions which I mean, are similar a bit to what I wanted to ask, but there are a few questions I can still ask you. So let's start maybe with the deep learning or machine learning part, which I found very nice. It's true that this type of model or let's say approach is quite heavy, I guess. The start, you have to deal with a lot of parameters to play with, figure out what range of values, etc. You describe it quite well. I mean, very well, even in your manuscript. And in the end, so you mentioned that you let's say you choose to narrow down the approach by focusing on input and output sizes. The rest of the parameters you mentioned have been played around a bit, and but you focused on those ones. Okay, can you just comment a bit on why, and can you comment on how? I mean, it's linked to a second question a bit, which is interviewed, but how comprehensive the approach can be made for this type of problem, because it's complicated. And okay, just to
So yeah, in the end, there are a lot of parameters to train with. With this work, we adapted a network that was originally done by May et al. 2019 for Earth observation, and we adapted it. We added a dense layer in the middle to be able to improve it a bit and also to extract these latent dimensions. So of course, there are many parameters. In our case, what we did was to focus on the input and output, because this was what was mainly changing from the work from May. So in their work, they use hyperspectral images from the Earth. Of course, the spatial resolution is much better. They use it to characterize the composition of different fields on the ground. So we knew that the input area would be different because they are using meter resolution and we're using kilometer resolution. So this is why we were playing around mostly with the input and output. Then there are so many parameters that you can change. You can change the number of layers, you can change the size of the kernels, you can change everything. So what we studied was, well, the patch size is the input size, the latent dimensions numbers is something that is very important for us because it's the way we are reducing the data. The number of clusters, clustering algorithm, and we also changed the number of filters. So how many steps we go in. And what we saw was that changing from 2 to 3 did not significantly improve. So then we stopped there. And then, yeah, for things like the activation functions, the weight decay, I did not go into playing because already this was creating around 50 models that take 4 hours to train. So in the end, I did not spend more time on this once we reached a good result, but yeah, you can spend years training the model.
Yeah, exactly. Actually, that's a point, because I wonder to what extent this type of approach can be progressed or improved by applying some automation or some artificial, some intelligence in this tuning. So, I mean, I think this is an interesting point. Now, the results you have are impressive. I mean, the identification of the pyroclastic deposit. I'm not an expert at all in this, but look extremely precise. Okay, that links to maybe the second question, which is you have trained. You said, correct me if I'm wrong, but you have trained the process over the whole planet at the end. First, you started with the identified deposits, and then you train over the whole planet. And I was not too sure to understand if you got, so how many errors or false positives you obtained, if you obtained any, and how do you handle that?
So this is a tricky thing. It's true that I trained it for the deposits and I applied these results for the deposits, but then for fun, and I didn't publish this, but I trained it on the entire planet to compare with the work from Emma, and it compared pretty well. And it's true that in some, so the issue is that we are detecting the deposits by this by these changes, by these layers that are going from the inside to the outside. This is something that also happens for craters. So since I trained it for the deposits and then I applied it to the entire planet, if you have a crater that has also this same change in properties, it can also detect it as a deposit. So I think if we wanted to use the network to actually detect craters, it would have to be trained. Maybe not, this is completely unsupervised. So maybe it would have to be a mix to add a bit of supervised knowledge to say, okay, this is a crater, this is a deposit, this is a hollow. Because since everything on Mercury is basically flat and doesn't have features, then it is using this spatial information to find it. So if we want to differentiate very strictly within crater, hollow, deposit, we have to train it and tell him, okay, you are going to find information in this data, but know that this is a hollow, this is a crater.
Okay, it makes sense. You have to add a bit more information or knowledge, basically.
Yeah.
But okay, thanks. Also a point which is how the deposits are spread over the planet. Maybe it's a naive question. So when you show, I mean, there's a map where you showed the, yeah, exactly. So towards the poles, there are less points. So those are because of observations, limitations, I would say.
Yeah.
Okay, and okay.
Well, so we remove the high incidence angles.
Because qualities are, I guess for BP Colombo, you for BP Colombo, you expect to cover those areas, or is it something that, or the poles are still going to be more difficult?
For the incidence angle, it's true that it's depending with the planet. So this will still be an issue, but with MERTIS, we can look at them with the mid-infrared, and in this case, we can look at them in the poles as well. And the thing is, in the North Pole, I didn't talk about this that much, but there is the northern smooth plains, and actually, in this case, there are less deposits identified there already at lower latitude. So for the Northern Pole, already from images, it is less expected to find these, or they have not been found so far. There are a couple of them just in this very large extension. From the Southern Hemisphere, it's true that we have less data. So there, it might be possible that at least with images, they are detected. And then the spectra, we will see.
All right, okay, super. And I think you said it, but you mentioned that there was not too much of a dependence on location. I mean, let's say the variability of the signatures were not too much dependent location. So even not latitude-wise.
No, we don't find any correlation. It would have been maybe expected because the rates of weathering are different depending on latitudes and also on longitudes. So we were looking for that correlation, but we didn't find it.
Funny. Okay, okay, thanks. I also appreciated that, or let's say it was a good learning for me to see that the clustering part makes a difference. So you do need this type of thing. So we are so I'm more coming from the space physics perspective, and there's a lot of work done, for instance, on solar, or well, how should I say, prediction of CMEs and you know, flares and propagation, solar system, etc. And yeah, I mean, this type of approach I think is very interesting. Or I mean, maybe the methodologies are a bit different, but this clustering point is very relevant for what is done more in my field. But it's a starting. I think what you do here is quite mature in comparison. So in any case, I want to go to the temporal evolution. So where you see that there was a point I was wondering, maybe it's a naive point. You've been commenting on the let's say effect of space weathering, on the time scales of space weathering effects. And it was not clear to me whether there are geological effects, so not space weathering, but which are contributing to the aging on similar timescales that, yeah, can, you know, be components, but because then the conclusion is, yeah, space weathering is a major contributor. So basically, but it means really there's no
since Mercury doesn't have an atmosphere, it is mostly the impact of the space environment that will change over time. There is, for example, there could be the effect of having, so there are tectonic features on Mercury, and there are some of these tectonic features going through vents. So, and it is not completely clear if the vents are happening after or before the tectonic feature. So this is something that can change the apparent aspect of a vent. But in terms of weathering or in terms of changing the spectral properties, it will be mostly the exposure to the space environment.
Okay, well, that's then explained very, very nicely. I think on the, I was very interested as well on the experimental part. Maybe I understand a bit better this part. So it's the angular effect is prominent. I think Patrick Pignot already made the point that logical continuation is to study radiation and the relative contribution. There's one thing which I learned from asteroid, let's say, simulations, or which is the impact of porosity. So porosity is a parameter that can have an influence as well. And of course, the gravity is not the same if we compare small bodies with Mercury or the Moon. But yeah, maybe this is something that is, I mean, small comment, but you know that can be looked at as well. In fact, for asteroids, it has, I think, quite an impact.
So here we were changing the grain size, but it's true that changing the porosity also will have a similar effect in reducing the absorption bands.
Yeah.
And for Mercury, we have some colleagues in Finland that are looking at the packing density, which in the end it's kind of a reverse of the porosity. They found that Mercury has a porosity of around 45. I remember now if it's 45 or 55, but around that percentage. So I think it would be interesting to, on top of having analogs that are close in grain size, to also have them close in porosity. And we have some people here in the lab that are doing experimental work on porosity. So this could also be an interesting suggestion for ongoing work.
It's I mean, it's not easy to do, I guess, but okay, well, I don't know. I mean, it's an interesting point, but yeah, I think it's a suggestion at least to follow. Okay, I think I have another question, which is a bit, let's say, contextual, but what you learned on Mercury is great. So are there other, if we extrapolate a bit at the solar system scale, where would you think there's an interest to apply the same approach? On which solar system body?
For the lab or for the?
Well, I mean, in general, I mean, okay, it's volcanism, so not every planet has a, well, I mean, but you mentioned for I know, for Mars, for instance, maybe this approach is not too relevant. But what about, I know, other moons, even moons of giant planets, and other types of surfaces, I know, more water-based.
So for now, we've been applying to a fairly dark and featureless bodies. So again, asteroids are also like this. So this is something that we could also apply to asteroids, for example, and to data return. Nowadays, there are many remote sensing missions to asteroids. And then, of course, the Moon is very similar to Mercury. But then if we go just for the deep learning algorithm, this is something that can be applied to anybody. It will just, so it has been applied to the Earth, so it can work with absorption bands and different terrains.
Definitely.
So of course, I would love to see this a similar work on Enceladus or any icy moon. I think it can show very interesting features. And then regarding the timing part, I think it's something that has maybe not been done so much. So in other, for Mercury, I would be pretty excited to apply the same thing for hollows. So if in other bodies we have the same question, whether how the spectral properties are changing over time, I think it would be.
Well, it's a great, I mean, you mentioned Enceladus. I think it's a very, very interesting case. I think that maybe the spectral change might be fast compared to Mercury because you got these plumes which are continuously populating the surface. But people are looking into this, and it's a hell. It's super complicated to get consistent information from the reflectance. So I think this type of algorithm can be extremely relevant. Okay, I think I still had one question. Right. Yeah, maybe just a quick suggestion, which is, for instance, for flares and CME propagation, there was a work done by, I can't remember the author now, but he was able to improve his predictions of CME timing, arrival time to the Earth. So he trained neural network, etc. And the way to improve was to add a physics-based model to the learning of the neural network, and that's quite efficient. So by doing this, he reduced the uncertainty by a large factor. Okay, I don't know how much that can be applied in that type of context, but yeah.
Yeah, no, it's a very good suggestion, because here it's true that we were using an unsupervised because we don't necessarily have this physically based
exactly.
But with Bepi Colombo, once we have a bit more knowledge of, or even with the lab, of how different spectral properties change with irradiation doses and different weathering doses, I think it's very interesting to apply that and combine it. Yes.
Well, it was very efficient. So, well, thank you. I stop there.
Thank you, Sylvestre.
Yeah, well, thanks so much. I guess I'm the last one, and all the questions have been asked. But first of all, I would say that you did a great job. Excellent. I read your manuscript. I like it. First, I saw that the introduction part was too long, it's many chapters, but then I realized that it was very good because I learned a lot. So congratulations for that. And same on your oral presentation, extremely didactic, super figures, good work. Yes. And you've covered a lot of different themes of planetary science, so it's good. When often I see some machine learning work, that scares me, okay? As you know, these techniques are very good at finding correlations that do not exist or have no physical meanings. And I want to congratulate you because you did it the right way. You didn't cover everything. And you picked up one topic. You train your algorithm very well and try to find what you wanted to find. So this is very important with machine learning. But then comes a question to me now is, well, once you've done that, you could have used other data sets in your machine learning process. And these techniques are very good to handle multivariate approaches. You could have used, I don't know, GRS data, an albedo map, or even is there a thermal inertia map on Mercury? There's a kind of thermal inertia map. You could have used other stuff. Why didn't you do it? You just stay to your messenger data.
Yeah, so it's true. So one of the things that we thought at the beginning was to combine, in particular, MDs and masks. So the images that provide this spatial context and the spectra. To be honest, we didn't do it because since this already worked and provided the outcome that we needed to continue the research in the timing of the volcanism part, it would have been quite a lot of time to incorporate the data sets. But this is something that we discussed at the beginning, to include MDs, to maybe even Bela, which is the laser altimeter, to have also the detection of the events included in that. So I think it's a very good idea. And for future work, I think it's a very interesting idea. In this case, since we already will have symbiosis, which acts as a mix of masks and MDs, luckily this is already incorporated in one. But it's true that adding composition, for example, composition in this case was not possible because the footprints, if I go back to the composition map at the beginning, as you can see, the detail is not huge. The footprints are very large because of the very eccentric orbit. In particular, the southern hemisphere, there is almost no detail, and in the northern, still the resolution is very, we wouldn't have any information for composition. So the real possibilities were MDs and the laser altimeter. And I think this is something that with Bepi Colombo, if we have symbiosis and we already add also the digital terrain models, it would be a very good incorporation, yes.
I agree with you. I think it's planned for future work, I'm sure. Another question is something I'm puzzled about the time scale. Of course, it's kind of your conclusion is, okay, how old are they? And I'm surprised to see error bars of the order of nearly 1 billion years. It's not the case usually in a solar system because we have crater counting, not of the, I'm not talking, I know you cannot do crater counting of the place itself, of the area of the pyroclastic or volcanism, but around. And it's me, I don't know enough of crater counting on Mercury, but can you relate that? I mean, can you try to do better in terms of having a timing of all these events?
So the thing is, since the eruptions are very likely younger than the surrounding terrain, the input that we have from the age of the surrounding terrain, they're just an upper limit. And actually the first works that were from Gauge et al. 2014, they were looking at the spectral properties of the deposits and they were correlating it to the crater degradation. So the crater degradations, they do have associated a time scale, again, with error bars of almost 1 billion years, but they do have associated a time scale. And what they were seeing is that there were no correlations because of course you're seeing, okay, this deposit is in a crater that is 3 billion years old, but maybe the deposit is 1 billion years old. So I think with error, with crater counting, it would be a similar thing. So crater counting in the deposits does not work, but crater counting around the deposit would provide the age of the area where the deposit is, which might be billions of years older than the deposit itself. So this was a bit the challenge. And I would like to provide closer estimates. One of the things that I like is that, for example, here in this plot where I show that the properties are going towards the values of ejecta. In this case, this is actually from two ejecta from the Debussy and the Kuiper craters, I think it is. And actually these two craters, they have been dated around 300 million years old. So if we approach these values, we could be kind of pushing even a bit closer to the 300 million years instead of 1 billion, but still we cannot provide any error bars better than that.
Yeah, I understand. And another question is, you mentioned it in the introduction, you mentioning in the conclusion, everything about volatiles. Of course, you need volatiles to create your explosive volcanism, but you also mentioned that we need volatile. There's volatiles in the exosphere, I mean, mostly helium and sodium, I guess. You mentioned recently nanophase carbon to express the darkening. You didn't mention so much, but there's volatiles at the poles of Mercury. Do you think, now step back, if it's one story or are they all different stories? I mean, it's really puzzling to have so many volatiles so close in a solar nebula when Mercury was formed. And especially when we think we're probably missing half of the planet, at least a good part of the crust. What do you think?
So I think there is a story, and of course, like the volatiles, it's something that it has been observed. So luckily, it's not something for me to demonstrate that they exist and that they can form the volcanoes. But yeah, so volatiles have been present in different forms, and they interact between each other. So now with Bepi Colombo, they want to observe how the poles might be feeding volatiles to the exosphere, and vice versa, how the exosphere might be transporting volatiles through the planet. Also, hollows might be feeding volatiles to the exosphere. but hollows might be forming from the volatiles that are exposed by the volcanism. So everything is kind of connected together. And then, the final question is, okay, how are these volatiles there? And there are different theories. Can they be brought by impacts? Can they be originally there? There are now works looking at how volatiles can be retained in a highly reducing environment, because mercury was formed in highly reducing conditions where there was not that much oxygen available, and they see how sulfur will be available in those conditions in an easier way than if it's formed in a more oxidizing environment. So I think there are different aspects that play importance here, and the fact that volcanism can extend later on, it provides just some more information for the interior thermal models that are trying to understand how the interior of Mercury was evolving. But I think, yeah, it's a complex issue, and I do think that there is some sort of history here that hopefully Bepi Colombo will help in answering.
I agree with you. It's probably the most interesting part of the science, the volatiles budget, where it's coming from. Are they connecting to each other, the different reservoirs? Yes, indeed. Just Kathleen mentioned it about weathering. Of course, we keep saying that Mercury is like the moon, or it's a different moon, where the space weathering should be the same, more or less, initially. Except, of course, there's a magnetic field that could make a few changes. You mentioned nanophase iron, which is the one we're thinking to darken the surface of the moon. And now you say it could be some micro phase iron. And I read in your manuscript there was a factor 2 to 6, I mean, between the moon and Mercury. And I'm not sure, even if there's less iron on Mercury, I agree. I'm not sure it's a Dev Bluet probably result. I'm not sure to understand why the ratio of nanophase to sub-microphase iron would be different. It's kind of strange.
This there's a work from Lucy and Reiner in 2011. They look at it, and it's thought to be due to the different temperature. And since Mercury is exposed to very high temperatures, so this ratio, it's referred to the ratio of submicroscopic to nanophase, microphase to nanophase iron particles. So meaning that on Mercury, there will be more microphase iron particles than on the moon in that ratio. And this is linked to different temperature, because since Mercury, it's heated to very high temperatures, it's thought that these particles will agglutinate, and therefore they will form these larger grains of submicroscopic iron. While on the moon, you don't have these high temperatures forming this submicroscopic iron.
So be driven by temperature. Okay.
Also, by impact, it's thought that the higher impact velocities, they will also, it's another of the factors that are thought to form these larger particles, but the agglutinates.
With regard to that, you seem to mention that the gardening rate seems to be larger. I remember on the moon is what, 1 meter per billion years? Mm-hmm. Here you mentioned a few meters.
So the studies that have been done, what they show is that although the impact velocity is higher on Mercury, the resulting gardening depth is a little bit smaller on Mercury than on the moon. And this is linked to the fact that Mercury has a stronger gravity. And therefore, in the end, the gardening depth, it retains a bit more of the particles, and the gardening depth is a bit less, but very similar.
Okay, well, thanks so much. One last thing is, how is your model applicable to Bepi Colombo, which is critical? Because you're searching for a very, very faint signature. And you've been lucky because you've been working on the shoulder of the people who have processed the data extremely well, thanks to you. And we already know that Bepi Colombo data will be very different. Okay, one is a point spectrometer, another one is an image spectrometer. My guess is nothing is applicable, but everything is, in the sense that there will be, when you ask if they could be taken the observation under the same viewing condition, which we need to do to compare. It's kind of the ground truth, I mean, spacecraft to spacecraft comparison. But my feel is that the Bepi Colombo data set will be so different that it will have its own life, and it'll be very hard to compare it with, I mean, everything, just a small change in a response function, as well as you can correct the response function, will never be good enough to match the two data set. Well, have you tried to ask Bepi-Colombo people, we want your absolute calibration to be to X% accuracy, not precision, accuracy, to be able to match it with what we have. Do you have a feel if it's even possible to compare both data sets?
That's a very good question. I think the comparison, of course, it will be very different. And to be able to compare, we need first to take measurements in the same conditions and of the same region in the same conditions. And this is something that hopefully we will get. And regarding the calibration accuracy, I cannot really comment on that. I hope that they will do the best possible job. I hope that they will also get the observations that they need for calibration. And yeah, let's see once the data arrives. But as I said, I expect it to be different, and I expect it to show things that maybe we're not ready for. And
yeah. My guess is going to be very different. And one last about your experimental work, because I think it's very important what you did is to bring what I would call a standard, a new standard for mercury studies. And remember that it makes sense as a new standard if you can produce a lot of it and distribute it to many labs, because it would give people a chance, like a GSC1 for Moon and Mars. So we have these standards we use every day. Are you close to have something you can massively produce and say, now we have what labs need for the work?
So this particular one, it's complicated because it's a meteorite. So
I know
it's very, very limited. There are works, I'm not leading that, but there are works, the people in DLR, they are putting this initiative together. So they're creating an analog that they can distribute across different labs to do cross measurements, to perform different experiments on the different analogs. And I think it is important to go closer, both in composition. Here we're measuring grain size, porosity, but also, for example, albedo. Here we have a sample that is a bit brighter, and because it's missing a bit of these opaques of this carbon. So going closer in all of these aspects. For our analog, complicated because of the obrites of the meteorite. I have a little bit here. We can try to do something with that, but yeah, I think it's a very important point what you're raising.
Well, thanks so much for your work, and thanks for answering the question. I can see that you've read a lot, and you have a good set of papers, and you cover a lot during your thesis. Congratulations.
Thank you.
Thank you, Sylvestre. Before handing the mic to your two supervisors, I would also to congratulate you on your work and the quality of your manuscript, especially. It was a very great pleasure to read it. Apparently, you took also a great pleasure writing it, right? Because I may have one question that was hinted by Fabrice and Sylvestre in the last questions. In how much extent can you maybe combine both your laboratory work and your current algorithm to predict something for Bepi-Colombo in terms of observation geometry? What would be the best suited for detecting different phases and different deposits on the surface of Mercury? Have you done that? Do you envision to do that?
Thank you. So for now, what we have observed and what I'm trying to pass on to Bepi-Colombo is this importance of the emission angle, and especially for the samples that have more magnesium. And since we see that on Mercury, there are also very strong differences between the high magnesium region and the low magnesium northern plains. This is something that if we have to perform this calibration and these measurements at different emission angles, let's do it in the high magnesium region, because it's where we expect to have this stronger variability. Then in terms of comparing directly to the spectral data, it's a bit complex because we have differences in albedo, difference in grain size. So for now, it's more about getting the trends that tell us where the remote sensing is going and how we should be creating the observations. And then hopefully once we have this information, we can then go back to the lab and learn a bit more about the effects of ion irradiation when we have also better constraints with the composition mineralogy. So for now, it's about providing the trends. And when we have Bepi Colombo, we will create better analogs also in mineralogy and remeasure them and understand them better.
Okay. Alain, Sébastien, the floor is yours.
Good, thank you, Mireia. It's also part of my duty, I guess, as your collaborator to make sure the jury is happy. And so Geddes is Irish, so I don't know how to pronounce that. Yes, we convinced the co-PI to make some off-pointing measurements. So we're getting there little by little. Although, I mean, whatever we compare with Messenger, as Sylvester expanded, it's going to be quite different, but there is this fraction of the wavelengths that is different. And that has been a good stimulation for your work. And for the samples, yeah, we are about to create 1 milligram, and that's a lot. The difficulty is on these reducing conditions for forming the rocks on Mercury. You can't create that on Earth. And also the sulfur, which is highly volatile. So it makes your samples at the same time difficult to create and preserve. And we're lucky we have some lab that working on this, but the work we've been doing together has stimulated a big impact and response in the community. And nowadays there are various initiatives going on, and it's pretty good news on that. I have a few points that maybe I can say. I've been lucky myself to start working with you before anybody else in Lira here. We started to work together during your master, during COVID, which was, well, quite an experience, so to speak. It was like trying to solve how we could explain features that everybody was projecting on a 2D maps when you know the comet Churyumov-Gerasimenko cannot be projected on a 2D maps. You did a good work, and few weeks after we started, you already were contacting people at APL, telling them their code were wrong, and that was the way to deal with the stuff. And I was like, who the hell is this? Alain, we need to keep her. We managed that. That was pretty good here. I think I guess the audience should not only appreciate the amount of work that you've done, but also the diversity of the things you've done. You finish your thesis with 3 papers published. The last one this week, important. Not a lot of people can say that, including myself. For sure. So that's something quite important to keep in mind. Rapidly during your thesis, you've proposed to Alain and myself new approaches, deep learning. Like Sylvester, I was very skeptical just because this is something you don't understand, so you're skeptical by default. You defended it, you convinced us, and we followed you. At the time we started to do this, you did some extensive work on the literature, which was in fact very fast because there was like barely 3 papers dealing with machine learning on planetary science. So you really started, you were part of the people that started that movement. It's quite important to do. Like Patrick, I liked your mess plot showing a bit of the diversity, but I don't necessarily agree with what you said, that was not necessarily a mess. It was just showing the creativity you had at the beginning of your thesis, putting new plots every bloody week. And I was like, I could not keep with that anymore. And so that's not a problem. I mean, it's part of our work to explore directions that sometimes fail. And we did quite a lot on this, but at the end we get to something that makes sense. So that's quite pretty good. One point that the people will not necessarily appreciate it is how many times you mention, I don't understand, I'm not a geologist. Then, I mean, for a geologist, I think you've done pretty well diving into mineralogy, various rocks. She started even in 3rd year to dare mention names like pyroxenes, like pigeonites, and I was like, oh my God, where are you going, Mireia? And now I think, well, maybe not now, but at the coffee, you can tell us. I'm sure you had quite a lot of fun crushing those meteorites in pieces, no? You will tell us that later. People do not need to necessarily understand all the background of work that you've done outside of the thesis, which if you want, I would encourage you to go, just Google things, you'll find things you will not believe, but yeah, no, that's true. It's quite impressive. But also to highlight that during your thesis, you've been selected to work with the Albach Summer School, which is a very important school. ESA is part of it, financing this very well. And you've been, as far as I've understood from outside, not following anything on this, that you've been one of the leaders in designing this exoplanet mission proposal during the thesis. Takes time. You went to Belgium to make these CDF studies as well. So that takes time out of the thesis. So it's quite important. And there is many other things that kept you busy outside of the thesis. So we could have done everything that your wonderful people have asked you to do. Next time, we'll try to do it that way. And the things that I would like really to finish with, because that was at the same time for me, I was like quite happy, but I was at the moment even more happy for you. Was very few months ago, very recently, was in one of the instrument meetings from BP Colombo, which I was there supporting as an operation scientist, trying to understand what the instruments want to do. And at some point, they started to talk about the science toward the end of the meeting. And in this meeting, Jim Head was part of that meeting, which, at least for me as a still medium young scientist, has been always in my radar from the beginning, big figures in volcanism and everything. I don't think Jim realized I was in the meeting and then mentioned, well, there is a paper that just came out in the literature from Leon-Dasi and their colleagues. It's fantastic. This is the example of what should be done. You guys should do this. Wow, I was like a bit shocked positively for you on that. So I think it really shows, to me, that's really my summary. It shows the impact of the latest work we've done on the styming of the volcanism, quite important. And there's nothing better than having these being told by your colleagues independently when you are not even around them, poking them to say something good. So this is really, I think it comes to the end of the thesis, and rightfully, because this is really the good work we've done. So we'll continue a bit of road together in the next couple of years, and I'm looking for that.
Okay, so it's I am the last. I will not be too long. So just to tell you, congratulations, Mireia. I am here also to give an overview of your work here, not only today, because it is only the emerged part of the iceberg. I would like also to enlarge our view for the jury and for the public. So first, when you came, and Sébastien told me that we have a good candidate for our thesis. You came but without any background in astronomy and geology. And now what you can show us, you could speak with some expert, best expert in solar system in this jury. I am very impressed by all the gap you feel. You talk about the gap between Messenger and BP Colombo, but you feel also a huge gap at the beginning from now in astronomy and in geology. I want also to say that apart from your thesis, you give some teaching, 64 hours a year. This is a huge work. You have a role in Symbiosis team as an associate scientist, and you even have a job offer from the team in Italy that you decline. And it is worth of mentioning that you have already a job, permanent job now at ESA. So it is also a great achievement. You are also part of the BP Colombo Young Scientist, and I think you will continue maybe. And in this thesis, you have this multi-approach, interdisciplinary approach, lab, orbital, modeling. So it is a good, very good achievement. Sébastien mentioned, but I would like to say again that you filed a patent in Netherlands, an extra work. You did, you participate to exoplanet paper. So everything is very impressive for me. And you have also some difficulties for the lab experiment, but despite that, which was beyond your control, you were able to manage that, and the final result that you show are very impressive. And last, I would like to say that you produce a very nice didactic manuscript with, I enjoy very much your figures. It's very synthetic and very pedagogical. So I like to tell you that you have a real talent for teaching, and I suggest you to teach classes, whatever your final career, because you are really good in that. So congratulations again.
Thank you. Any questions in the audience? No? Okay, so that will close the public session currently. So the jury is going to deliberate in this room. So could the audience please leave the floor for about 15 minutes or so, and we will call you back. Qu'est-ce que tu veux dire? Oui. Oui, on peut parler en anglais, je pense. Okay. Yes. So yes. So he's going to switch off